So 100 kilovolt is given here. 1 plus ion will be 100 keV plus 5 keV here, whatever, 4, 5. And if this is 2 plus oxygen, when 2 electrons are removed, it will be 200 keV plus 5, whatever added there. So that is how energy is varied. And you can continuously varying from 1 to 100, and you can have ion implanted at various depths. Application part is really more clear. Nowadays, due to this nano technology, people are asking for ion beam focused at nanoscale, because you want to have a nanometer scale device, a nano dot, nano PN junction formation. So what is there? Earlier Taylor cone was known. Extracting Taylor cone, actually here by typically gallium source is used, and there can be many various kind of species. And here at the ion source itself, this becomes micrometer, fraction of a micrometer. So when it goes to the column, this is the focused ion beam column. I will show the actual column later. So it gets focused to few nanometers here. That is the beauty of that. And with this SEM, one can see also by electron spectrometer, one can see this. And then this detector seems kind of secondary ion mass spectrometer. One can see the ions which are scattered out. So this way you can have a sample, and sample is typically moved in nanometer scale. To move the sample, one needs a piezo, translational state. And this is the direction it has moved. It is quite affordable, within 5 to 8 crore rupees. One can have his own lab. One can, as per their requirement, one can do imaging. As I told you, this is actually the ion beam system. Very compact, made of neodymium, iron, boron, magnets, and this focusing element. This is liquid metal ion source. This source special, and at the tip you get few nanometer, 2 to 5 nanometer beam. So one can make a device of that kind of dimension. And what you can do, if one increase put the light low intensity, one can image it. One can mill it by increasing the intensity of the beam number of ion setting. So you can mill of nanometer scale. You can see the image, how it is formed, where it is formed. And if you want to have a contact, so one can put a precursor molecule and break by ion beam and make the contact in nanometer scale. Because nanometer device needs nanometers contacts also. Okay, so this is how it works. So this is the next version. This new version has come with quantum devices, quantum materials. Things is that single ion multi-species positioning source. This is the famous UK National Ion Beam Center. We have a lot of interaction with them. University of Surrey. So they, with a company, come out with this Ion Optica. This is extensively being used in the development of newer, exotic, unique devices and sensors now. So coming back to this, our actual when we go for megawatt kind of ion, we can use for irradiation. We can use other issue, exotic phase in materials. And nuclear physics also, one can cross the Coulomb barrier, go closer to the nucleus, and it works. So early 70s, India, this is the time actually people started moving major developing countries and developed countries, no doubt. Few years gap, you can say, moving for large accelerators. Before that, this is a Calcutta variable energy cyclotron centers. I just was in college. At that time, we used to go also to visit there to see around. But this is a photo provided by Professor Bhandari, director of the center. And then here, actually, India took first plunge to the hundreds of mega electron volt ion beam facility. And that point of time, it was just a big imagination for a country like India, which is growing slowly economically. But most of the thing developed indigenously, the way we develop a lot of things here now. So, and this is technology develops. The Ranchi steel factory there, they actually could develop this big D of the accelerator. He is the founder director Divetia, Professor Divetia. So, and the team, they worked day and night, and really it was a great achievement. And on 16th June 1977, actually first beam they observed in the night, 8 MeV alpha beam obtained. It is Professor Divetia's own handwriting, cyclotron testing, and generally all this big system, big thing happens in the night. Sometimes deep in the night, your big ideas also sometimes come when you are thinking coolly in the night. You are not able to solve the problem, mathematical problem or something daytime. Due to so many perturbations, you can easily sit down in the night and you can say things are solved. So he beautifully wrote no testing tonight. Yes. That day holiday for the night, at least for the people who are working day and night. And general shift is declared on the next day. So that is how historically things happen. And this is the cyclotron, the build. And it is a picture of recent with repainting and all those things. It is still working. Today also it is working, producing fantastic results, hundreds of PhDs, and it is one of the great facilities operating since 1977 continuously. Electronics and some of the control vacuum systems are refurbished and sometimes replaced, but main heart of the system is intact. So a system made properly, it works for 50 to 100 years. So, and this is the kind of beam it is producing from the beginning. The proton, it started typically up to 20 mega electron volt. Actually, an accelerator, always energy is put in electron volt in the sense how many charge, what potential it is developed. You can convert to any other unit. But this is the unit because all physical processes will take place in your electronics and all those things connected with EV energy or nuclear processes. All those things are put EV, so that is how it is put. And you can compare this 20 MeV, the Kurukshetra machine gives you 100 of keV. There is a megavolt, this is a big factor. And then argon beam was available up to 350 MeV. So this is a deconfiguration. Various you have studied cyclotron in starting from school, so you know how it works. But this is actually in a big one, mega scale cyclotron. So that is the beauty. Then Van de Graaff accelerator was another thing was going on. We had a big one in Bhabha Atomic Research Center. India beauty is that India actually kept a space with this few of the things like space, nuclear, all these niche areas, and mathematics, statistics, physics. Top physicists were there around. So, chemistry like that, top chemists were there in the country, biologists. Biologically now we are one of the leading countries, means particularly in medical biology. And then almost all aspects of molecular biology, almost aspects of biology. Similarly, physics also we have good say internationally. Chemistry also we have very good say. So that is the beauty of the planning our forefathers getting developed. So this Van de Graaff also you have studied, but let me explain one thing. Here actually ion source is placed within high voltage terminal. This potential goes to 1 MeV can go to up to 12 MeV typically, 12 megavolt potential it is there. So whenever you have to change ion beam, one has to shut down the whole accelerator, replace this ion source. And these are always positive ion source. How it works? It's a charge is carried by a belt. It is charged up. If charge is there, it is having certain C, B is well defined. Because you know, when you make this kind of system, it is having a certain C, and if you put on Q, and then you know what is the V. C equal to Q by V. From there you can control the V. But if one potential is taken to 20-30 megavolt, then it sparks out. So it can cause accident. So one goes to safety mode. So based on the design, it is having, typically it was designed for 1 megavolt, 2 megavolt, and best one were in the range of 12 megavolt, 15 megavolt. But we had in India 8 megawatt, 6 to maybe. So this is the design, and this is a real Van de Graaff in Bhabha Atomic Research Center, which is later transferred to the FOTIA, means a tandem machine. So this is how it works, and this is inside the dome. This is the column. So this way technology developed, and I should mention one by one this kind of implanter development. And first accelerator was developed by Meghnad Shah in Calcutta University. There are 3 oldest universities: Calcutta, Madras, and Bombay. They were the 3 major universities. Calcutta was first anyway. The other 2 came later. But all these universities, they are a good ion beam program. There, Professor Joshi started a big ion beam program in Bombay University, and in KUK, tens of KUK domain. And Calcutta, it was a MEV domain, because Saha was more a nuclear physicist. And here this Joshi and all, Professor Joshi and all those people, they were working materials modification, implantation. Kurukshetra also from 80s, they have big idea and going for accelerators. Even before that also, cyclotron also initially was supposed to be in Kurukshetra, which was later shifted to Chandigarh. But we had scientists passionate about it. We had this many universities, Delhi, then a lot of universities slowly developed having accelerator program in different domain. So that is how it moved. Later in the 70s, late 70s particularly, a tandem concept started coming in with negative ion source development technologically. Because all this is the difference between Van de Graaff and tandem. Van de Graaff is terminal, you have ion source inside, and potentials for 2 megavolt is used only once by the ion beam. Okay. In tandem, beauty is that you develop the potential, even if 1 MB, half the potential also. Ion source is outside, but one has to have negative ion source, which is negative ion source is technologically challenging. That point of time, it was highly challenging. Nowadays, it is reasonably understood, and we are making our own ion sources also. So negative ion source can be outside, so you don't have to open the whole machine to change the source. And then negative ion gets into the terminal. There is a stripper. It strips the electron from the atom, and the atom gets highly charged. Based on how many electrons it can be stripped, it can be up to 10, 20, 15, depending on the electrons available in the atom. And then that many times the same potential is used. For example, if I put a helium, 1 plus 2 megavolt potential itself is the 2 MeV helium. Whereas same helium, if I put here, negative helium comes here, negative is always 1 negative. Negative cannot be 2 or 3 charge state. Is there one can add maximum 1 electron to a stable atom. Quantum mechanically, it is not possible more than that. Cannot make any potential well. The electron affinity immediately vanishes after adding 1 electron. So 1 electron is given 1 MeV, then 2 electrons of the helium is stripped out. So 2 plus another 1 MeV into 2, 3. The 1 plus 2, 3 MeV comes out. So with half the potential, you get 3 times the energy. So that is the beauty of that tandem. So tandem gives flexibility, ion source is outside, and this. So this is a great development. 80s we caught up, and TIFR started to pass this in early 80s, and we got sanctioned in 84 for outside DAE system for the university system in tandem. But principle is same. Tandem you will find always UD means unit doubled. This 14 UD means 14 units are there, then terminal high voltage, then 14 unit again. So what it does, a negative ion is formed outside. It is cleaned by, as I told, the helium, this magnet, and put here. This when it comes here, it is in one negative 1 ion. It comes here with a 14 MeV energy. And when a stripper, typically nitrogen gas or any foil, carbon foil can be put on the path. For them, this is practically transparent. Only electrons are loosely bound to the nucleus. they get ionized, electrons are removed. So it becomes highly positive, and same potential is used to repel it out. So energy is gained twice, once by attraction to the potential terminal due to negative ion, once by repulsion from the terminal, positive ion. That is how 15 UD can produce hundreds of MeV. How? It is 14 UD multiplied by whatever charge state. Suppose I take 10 charge state, that's 10 into 14, 140. 140 plus 14, 164 mega electron volt. So this is tremendous gain with this modern technology, because in the handicap it would have been only 14 MeV always, okay, or 28 maximum. So this is the technology which came. Here the unit I told you, unit double, that units are typically like that. One unit, each unit can go up to 1.67 megavolt, but typically we consider worst case 1 megavolt each. And then we 14 UD inside this column, they actually ion beam gets accelerated, and then this yes, side by side I will come to IUSC later to finishing TIFR, because they are fast starter. And then they going for niobium cavity resonator for LINAC. LINAC is today actually luckily we caught up at that time, not going to cyclic accelerator, because cyclic accelerator there are other, when energy keeps going there are other losses like radiation and all those losses. So today, actually, everybody is going for LINAC for future accelerator, future planned internationally. Due to the fact LINAC, one can keep on accelerating each model separately. But there were two technology at this point. One is lead, which was slightly easier. One can do plating. And another was niobium. Niobium was very tough at that point of time. Only Argonne National Lab had it. And that actually, though we collaborated with them, there is no plating possible. So one has to have pure niobium, and then electron beam welding, all automated robotic process one has to follow to make this cavity. Then this TIFR LINAC facilities. This is at par with anywhere in the world, these facilities. IUSC started 3-4 years later, but we caught up almost same time with TIFR. We had the accelerator ready by end of 80s, 89. And we started giving regularly to user by 1991, like that. But we are going to our own experiment, testing, be sure that when we call somebody, there's no. But we had few innovations. We have put offset quadrupole terminal in the terminal, because we had a good, quite a few very good physicists involved in the accelerator physicists. And good thing is our founder director was a disciple, student of this Saha, Professor A.P. Patro, who came, he was SINP director also. He came from Science Institute of Nuclear Physics. So he was a genius and excellent person. We worked with him, learned many things from that kind of stalwarts in this field, and really one has to interact to believe the depth of knowledge person developed over the time at their old age. So he made a success, and it was surprising because people are doubtful whether in the university system this kind of thing can happen. Initially they gave some funding. As we progressed and we showed results, we got good support. And so it is a great program, and we wanted to have to prove it can be done outside system. But that is why our accelerator, anytime you walk in, you can, all the university can feel they are part of it. It is their property. It is a combined property, fully supported through EGC by Human Resource Development. Now it is Ministry of Education. So this offset quadrupole, actually there was some theoretical thing in Russian language, some papers, Uzbeki. Professor Patro told me, so we got translated from JNU, did all mathematics, and finally designed it works. It actually chooses the charge state at the terminal. I will not go into that. That everything goes in a defined loop of physics and technology. So this is our units, how it looks, being passed through that. And this, why I want to see it, this is a new materials. What is the material? This is the material is actually titanium and ceramic. Earlier that when accelerators are there, there used to be glass in between electrodes. This is a new definition was there. Titanium and ceramics are put together, put at high potential, high vacuum, And there is a solid state diffusion. You will be studying when you go deeper into solid state physics. Solid state diffusion, the atoms start diffusing at the interface. And that bonding is permanent bonding. No glue can bond like that. For that, what is needed? A high temperature, nearly 2000 degrees Celsius, and high vacuum in which it has to be put under pressure systematically. So that is the technology in this accelerator. It will remain working for 100 years or more. So this is that point of time it was a surprising technology. Today it is well established. Technology of yesterday today is part of life. So these are the resonator TFR went for lead. We went to niobium. And today, after 20 in this 21st century, all the future accelerators are being planned with niobium. The lead is discarded permanently, because the reason is that this niobium gives much more field, so same distance you can get much more energy. And second thing is that it is easy to maintain. Lead oxide forms, then it is no more superconducting. Niobium is that way inert. And third is niobium is very costly, no doubt. And third is for same electricity you have much more energy for spending same electricity, which matters for the, at least for the head of the institutes and those who are running for fund. So this is the indigenous fully developed niobium cavity. And I will show to it. This is how this accelerator looks. These are all latest technology. Nobody can. We put piezo control earlier as helium temperature. This works in superconducting phase. So nothing you can normal thing can be put there. Even controlling, we cannot put a pressure any gas other than helium, because it will be frozen immediately at helium pressure. Liquid helium. We have a huge liquid helium plant. This is 1, 2, 3 line. As money comes, you can keep on adding. So that is the flexibility. This is how this accelerator system, different components looks inside is built in the country. So we have now power of the building, electronics, control room of different sections of the accelerators integrated. And now we have so many accelerators, implanters also ECR based, multi-chromosinics based implanter. This is a compact implanter up to 50 kV. And this is a mass spectrometer, atomic mass spectrometer. I'll explain in the next this thing, RBS facility. So these are all in university domain available to you people for your PhD. This is next generation accelerator which started, which is going on another few years. It will be giving. It will directly feed beam to the LINAC. The peloton will be separately available. LINAC will be separately available. At this moment, LINAC beam is further accelerated by accelerator. This is a high temperature superconducting ECR. This is the world's first one built by us, and this is very famous. It is known as Piccadilly's internationally. Okay, and this is future program is going on at BART mainly. It is his mega science project, accelerator-driven subcritical system. So this actually in future reactor plan is that the accelerator will drive it. It first came from CERN director's initial idea proposal. Now it is matured and it is proven to be correct. So 1 GeV proton beam will be put with certain current. Then reactor will be subcritical initially. With accelerator will make it critical. So any problem comes, accelerator can decrease or increase the power or switch it off the reactor. Nowadays, last few reactor particles, Fukushima was a big danger because control went out of hand because it got flooded on those things. This kind of scenario it will not come. That is one thing. The biggest thing is that this long-lived isotopes will be made short-lived to that series of nuclear reaction, transformative processes. So that is why this is a future. All developed countries has big program and near threshold to be used soon. Another is coming ITER. I discuss a bit probably later, if time permits. This BCC after that accelerator, they have been working on their LINAC specialists, superconducting LINAC they have made. And last year, beam started coming out of it. It was a tough project because outside a few developed countries, nobody could build it. So India took it up and we went to sanction all kind of things. But finally, things are in shape now. And anything, any big project goes through a lot of failures, but that actually makes people stronger for the success. But ultimate success is always assured if scientifically program is correct. Because science cannot be corrected. Science is science, nature, natural rules. We have to understand and understand more. So this is the radioactive ion beam facility having LINAC and superconducting LINAC also facility. This is being built up on VCC. This is the first major accelerator lab. In university systems also, accelerators are coming, big accelerators, like it started with Bilaspur, having 3 megawatt, very state-of-the-art accelerator. But they have to develop culture of maintaining and using it. That needs a different kind of vision, but it is fully functional. And this is one of the highest beam giving accelerator and surprisingly, university people get surprised, but it is there. And it is fully tested. These are test results. We are involved. We always support university coming up any direction. And in the Science Institute, where Professor founded, and that Science Institute actually have a very modern 3 MB accelerator. They have come for astrophysics work. So this is also fully functional now. They are doing the experimental facilities they are growing. I'm telling children we have opportunities in various places. Internationally, CERN is actually driving the accelerator field. Large number of accelerator scientists and engineers are there. And they are actually planning 10 times bigger power accelerators. In fact, biggest accelerator today planned is the ILC. I am not showing it because that is not still funded, but conceptually I was also in design team. Design report, everything you can go and download also. Fantastic facility. In Japan, it was supposed to come. Our idea is all big scale accelerator. Actually, big scale means you have to add money. These are small scale if you see part by part, the same magnet, same thing, same cavities, but it is a large number over big area. Is that 100 kilometer circumference? So we have to put $1 billion here. Here they actually few millions will do tens of millions. There will be few billions. It is typically $6 to $7 billion project. But they are giving new ideas also, process. And all these accelerators are producing large number of Nobel Prizes. Almost every 3-4 years, the Nobel Prize goes to accelerators related work. And then this is inside the accelerator tunnel, 18 meters down. And then you can see people are cycling to see around. Where everything is fine or not before starting. So, and this is a new ITER. 2-3 days back, big news came. Actually, it is super critical going on. So there is an accelerator which puts the beam here, and then in tokamak it circulates. And there is a high current accelerator, neutron beam ion source they call it. And because before coming, the charge state is neutralized and put in that energy so that it can reach the core of the tokamak. And this is being designed, and we are actually equal partner of it. 7% of the share India has it. I just showed. And these are new generation accelerators are coming for high flux proton beam. This is a PIP to linear accelerator. Here also we have contributed by show some. How much time I have? So it is almost finished. Also that PIP one, latest one which is coming, there a resonator we have supplied and made it in IUC mainly, the niobium part, and stainless steel part is made in RRCAT, and BRC actually integrated it. And chairman of DI, Dr. Basu, came to see it, and when it was on the way, so you see the importance for it. Dr. Kagotkar also came there before shipping to, actually Fermilab paid us for this, 2 of them. It is landed at Fermilab. Okay. So which mean we are contributing in a big way, and this is the characteristics of various, the resonator made at Fermilab site. Fermilab did the characteristics, is not we are showing. And magenta is our thing. We are above many other big companies. Actually, except us, no lab actually could make full resonator, because abroad what happens, you can put your job to the private sector, because then you don't have so many engineers or so many things. And since this is available, India, if you give somebody, they will mess up, because we don't have that kind of support. Now it is coming. Now we are giving part of the job out, because this way we save our time, and then we can do something more innovative. Once we design, see, fine, then making many pieces, it is very routine. So a good scientist or engineers, after finishing it, they don't want to go and keep making it many. So, but proudly I can say this magenta line is on the top side, and our actually supposed to be operating in this zone minimum. It is far ahead, and it is going to high potential also. So this, to give the message, this he is a famous Nobel laureate and director of Fermi National Lab, Professor Linderman. He gave the name of the particle, God particle, all those things. He made a prophecy that thousands of years hence from now, archaeologists and anthropologists may judge our culture of that particular country or humanity by what kind of accelerators we have made. Whether we had an accelerator program. Means any country which is bright, developing and having a big pool of human resources, scientists and engineers, they have accelerator program. They may not have space program, they may not have nuclear program, but they have accelerator program. Because it is encompassing all fields. And out of around 35,000 to 36,000 accelerators around, 96% are being used in industry for commercial application for the benefit of the mankind. Yeah? So, and then for less than 4% actually is used for research and other activities. That is also for benefit, for knowledge and mankind. But they are just being used in the companies. India also we have many, but that is the beauty. So the requirements of wide variety R&D facilities are various synergies and justice have been driving large number of science engineers to keep motivated, working hard, bringing in new ideas and innovations to match the emerging requirements for science as well as for applications. So this is a very vibrant field, and the people are working, you'll find those who are contributing always happy and creative all over. Thank you. I acknowledge my large number of colleagues and different accelerator labs. Also, we accelerator people, we have a lot of collaborations, cooperations, and regular meetings. And thank you very much. So it is. So how do we move? We will have now question session or later? Hello? Should I stop screen sharing? If we don't take question now?
Yes. Thank you, sir, for thank you, sir, for explaining about the intricacies of accelerators from starting to the present day scenario in a very illustrative and simple way. So now I would ask a few questions which students have written in the chat box. I think there is the question from Umapati. The student wants to ask that, can we get some idea of medical sciences?
Very good question, and I have put in next talk. I will explain it, and this application next talk is more on applications in materials as well as applications in real life, and future applications also we are putting. So there I will discuss that in medical science, how it is there. But I can quickly, suppose you don't attend the next talk, what I can say, this accelerator beauty is that you can when ion beam interaction, I will show it, but one can calculate what is the depth and which ion beam will go and stop. Okay, and at what depth, how much energy it will put. So when we have medical this requirement, we have problem at certain depth inside the body and various region, brain or breast or various places in the physiological system. And accelerator can actually goes beam by variation of energy and species. One can go there and put all the energy where it is needed to solve the problem, and it doesn't affect other area when it is going, because you will see that we can tune the energy when we have this kind of ion beam facility having hundreds of MeV to a few MeV domain. We can control the process in human dimensions are well known within human body or head or wherever. It reaches, beam reaches and modify that particular, mostly tumor or that kind of problem. The accelerator has an extensive use in this thing. And for MRI and all those things also, as you know, this before this going for this scan, actually we have to have that energy generated like X-ray machine also. So they are also on electron accelerator, actually electron, high energy electron beam produce that photons. Photon production based on the what region we need. If we need a photon in the gamma, in the very 10 keV photon, then also use an accelerator actually to produce the X-ray, hard X-ray, 10 keV X-ray, 15 keV X-ray, or 1 keV X-ray depending on the case. And accelerators are using extensively to produce the radioisotopes. In fact, there are, as I told in the company, in our country actually, INMAS is producing large-scale radioisotopes only for finding, detecting cancer. So any hospital you go, there is nuclear medical unit. They are getting all radioisotopes from accelerator centers in various places. And so we have in Delhi one completely day and night working only with radioisotope production. Bombay. Reactors also produce some of the radioisotopes, but most of the accelerator beauty is that this you can control is in your hand, so you can control and put which is needed and what kind of quantity is needed. Large quantity you have to separate from them chemically. Here actually you can make exactly the quantity needed. And Calcutta also recently they have put one separate accelerator VCC only for medical use, no other thing at this moment. But they are supplying. Earlier, these radioisotopes used to come from abroad by flight, and rich people who could afford it, they could get some treatment. Otherwise, sometimes even richer people will go abroad and get it treated. But for middle class and common people, it was not reachable. Today, it is reachable. You can even all kind of nuclear medical facilities you can have in the country. And now we have one hadron therapy also facility that I will go through. That is the latest in the 100% cure of cancer and all those things are possible. Another one is coming to Bombay, and we are trying to have nearby Jhajjar.
Maybe we can take the second question by Kalpana, because Kalpana wants to ask how charge state is related to different.
Yeah, this is also a very important thing. This, charge state is actually, there are two types of charge states. Negative ion charge, when we call them, we have to have extra electron. Means all atoms are neutral. Suppose oxygen, I want to have a negative oxygen ion. What I have to do, I have 8 electrons surrounding the oxygen nucleus. Because proton number decides how many electrons will be there. And to put another electron in 8, they will not they don't have a defined orbit. So they can hold it for a few microseconds to few milliseconds, sometimes fraction of a second. Accelerator needs fraction of a microsecond to accelerate it. So the accelerator work is done as soon as it is attached. And when we attach it, actually we should have some electron affinity. It should have some potential, quantum mechanically confine anything you need and well. The shallow well also fine. Suppose helium, negative ion, it doesn't stay for more than few microseconds. But by few microseconds, maximum accelerators now for characterization I will show helium is used. Helium is most preferred beam. So within few microseconds, helium is accelerated and job is done before that. So that is negative. Positive ion is very easy to make. You part of the system, electron will be shaded. Because it is like a simple language we put for the high school student particularly. If you have a load, you can always unload. So you have many electrons, you can remove it, no problem. But you have a load and putting further load actually depends whether you can take it. So similarly, each atom is having an electron affinity. Or you can calculate also theoretically, or it is tabular form available. So whenever you see some electron affinity, there is certain way cesium, rubidium, charge, and electron giving elements are there. Earlier they used to be used for neutralizing the charge. So they put some electron on that, so it becomes negatively ion. And positive Penning gauge or any plasma sources are giving huge positive ion. So you just put, in fact, your this Kurukshetra is a positive ion implanter mostly. So positive ion production is easy comparatively. You just perturb it by ionizing the media. Then this extraction will take the ions, neutral they will not touch. So automatically you get positive ion. So this is how positive ions and negative ion differentiates. But accelerator, if you have tandem, you have to have negative ion source. If you have cyclotron, you don't bother about negative ion or this complexity. Positive ion do. If handicraft, positive ion will do. So these are the way things are distributed. But ion means electron has to be either added to make it negative or removed. As many as possible you remove, more energy you get. If you have 1 kilovolt potential, you have 1 electron left, 1 keV energy. 5 electron you remove, 5 keV. But you have 1 keV potential. Due to charge state, energy increases. So that is how one goes for hundreds of MeV using the basic principles which we studied in our school and early days in college. Here the technology comes, and there are many things connected to beam optics where within certain time I cannot go. In fact, how to contain them, how to focus this ion, those are all detailed beam dynamics has to be calculated. That is why otherwise so high-end physicists are not needed. Even if you see the top accelerators which can afford, like CERN, they have many multiple billion dollars. In fact, they recruit huge number. You people also can apply in some recruitment after MSc on various positions or the PhD also. They pay huge. And then important thing is that their brain is put on this new innovative development, doing beam dynamics, working on that. And very high-end physicists, top-notch physicists actually join that program because they work on futuristic. As soon as you increase the number of ion, it starts repelling. How to hold it? The beam dynamics, all those points are taken care of. All this problem, mathematics, equations with Coulomb repulsion, all those things are solved and optimized parameters. So positive ion source, ion comes that way. Though there is no ion, in neutral beam cannot be accelerated by any potential. So it has to be ion, positive or negative. So and anyway, you can my email ID is there. You can always contact me for going deeper and deeper. Okay.
Sir, I think students have a lot of questions, but is it okay if we take the other questions after your second talk? Because
I have kept it for you, whatever way you want, I will go along because that is the best.
Yes, sir. So, sir, it will be better if you continue with your second talk. And we'll take the rest of the questions after the second talk.
Okay. So before second talk, want 5 minutes break or something, or?
Sir, if you so desire, you can. Then we can have. Otherwise, we would like to continue.
Need it, but if it is fine with everybody, sometime listening same person for a couple of hours also become boring. Whatever.
Sir, I think students would like to continue with the lecture
because there are other programs also there. Okay.
Yes, sir.
Okay. So good. I'm going. I am unsharing and then sharing in one. Okay.
Okay, sir.
So it is coming.
Yes, sir, it is coming. Yes, sir.
Okay. This time it was fast. So this next one is interaction, a bit how it interacts ion with materials and different energies. And that helps in modification of properties and other recent applications. So I have limited time, so I will give few of the glimpses, which some of them will be very new and very interesting. And some of the routine things, the ion beam is being used for almost last 40 years extensively. The some regular ones I will avoid because we have to manage within the time, and I don't want you to be delayed in your other activities also. So my first question thing is that let us go back to how this energetic particles, ions, they about initially, because all kind of structures of atoms, earlier the nuclear and atoms were all messed up together, all kind of ideas were floating, but first impact came from Rutherford's that experiment which you have extensively studied at various levels, where it showed that even from the thin foil, mega electron volt particles, which are tremendous, which are moving with nearly velocity of light, they are gets deflected. It is alpha particle got deflected. So this alpha emitter actually initially he used, and alpha got deflected. That gives the him Nobel Prize also, and that actually gave rise to the real clear idea that nucleus whole charge is centralized. There are just electron moving around. That whole volume actually is sort of empty, and huge charge concentration is at the core of the nucleus. So that showed the importance of the high energy particles in science and completely changed the boost quantum mechanics like anything. The quantum mechanics initially went through a lot of turbulent phases due to a lot of old scientists, old schools of thoughts were not accepting, including Einstein also initially. Though his final Nobel Prize came from quantum mechanics of photoelectron effect, which is quantum process. And then many, every time happens, new ideas are always, people don't take easily. So it takes time to establish. Okay. So this is the background on which actually charged particles made a big impact. But today my things will be mostly connected to the materials related issue, because it is used in any particle physics, nuclear physics, low energy nuclear physics, high energy, many areas. But biological sciences. But biology comes under to some extent biomaterials or those things, we'll be covering a bit. But this is valid for all materials. Okay. So what is the important thing? As soon as you put an energy to the ion or atom, actually it just goes to a range which can be calculated, and it can be checked also. It matches. Calculations today is reasonably accurate. Okay, within depending on the case system, it is 1 to 5%, sometimes maybe 7% accuracy. You can place them close to the atomic site where you want them. So this is highly controllable. Why happen? This earlier, this all kind of things used to be put inside the material, something by diffusion, by heating it. putting to interface or putting some atoms you have to put inside P-type, N-type, silicon has to be made. One puts the dopant and put temperature and diffuse it inside. The diffusion will not be uniform. As soon as you give energy, it is highly controllable. It actually goes where it wants. You want it to go. And it can be raster scanned, and you can put a type of shadow mask or anything to put the locations you can put within. And initially in micrometer, now in few tens of nanometer scale, one can put the ion properly. And no effective, actually it doesn't change the dimension or anything, like when you heat it actually under pressure, or when you are pressing it, the dimension change. Here there you are not, temperature wise you are not increasing, so there is no change. And so the elimination, all those things are gone. But biggest problem is that it retains the bulk property of the host materials, but only except the place where it is doped, it gives the exotic properties there. But it cannot do for meters of this. So if you want bulk change, big quintals of the materials to be changed, it is not the good thing. It is good for making a device or in a concentrated area, few centimeter by few centimeter or meter by meter area, you want to change. So wafers up to 16 centimeters are also being used for implantation. And high vacuum process makes it slightly expensive. So actually, if it can be done by some other way, and we've established lot of process, and then so it can be done another way, almost similar like, and then leave it there, because it is a bit costly. They finally cost drives the utility also, and so relatively expensive. That is why high vacuum process, for high vacuum process. Why high vacuum? Because you have seen clean room. Clean room means you will see sometimes 10, 100 on a particular cubic meter volume, how many particles you expect. Here, cleanliness is even fraction of one also. Because here in a very high vacuum, there is no atoms is 1 in compared to atmosphere, 1 in 10 to the minus 12, minus 11. So this is the cleanest room, cleanest environment vacuum, where you are making your processes. Now coming back to this line, there are a lot of contributions from India, but first board started, then DETE, and it is going through a lot of modifications over time. Ion atom interactions. They have given it is found that when it actually moves nearly the velocity of electron in the orbit, if ion moves the same velocity, then they actually impulse goes for longer time. So it is mostly energy loss goes to the electronic system. And if it is moved much slower than electron will have many, semi-classical process. This electron have many rotations compared to time it moves around. So it neutralizes it. So electron doesn't get affected. So it goes elastic process. It actually, if it hits, by chance it's in the impact parameter, it comes along, the atoms get displaced. Then this actually happens due to nuclear energy. Though there is no nuclear excitation or nuclear process, nuclear name came because earlier movement of atom as movement of nuclear and atom used to be mixed up in vocabulary. Like, atomic energy commission, actually it's a nuclear energy commission. Okay, so that kind of scenario, if historically N is given, but to physics wise, it is this clean Coulomb potential is effective, and then this is actually elastic process, elastic transfer. But here, when they are exciting, ionizing the electron of the individual atom in the material, it is inelastic fully. The Bohr method came with the first their formula, then it is revised and corrected to the other corrections, particularly relativistic correction is very important. So what happens if you plot in a different way, actually this is a log scale, so you have to set your mind scale similarly, because this distance is not equal to this distance. This distance is this much length is around 1, 2, 3, 4, 5, 6, 7, 10 to the 7 times larger. So it is squeezed. Okay, energy scale. So it is taken from your 10 EV to 10 GeV scale. So this kind of scale cannot be proved. That is why we go to log scale, in science. So this whole scale, if you see, is around 100 kV domain per AMU. These typical domains, 50 to 100. The actually elastic process picks up. And then as energy goes so fast, the actually elastic process actually falls down and goes to zero. And inelastic process builds up after this typically 1 MeV to 10 MeV domain and goes up to few hundreds of MeV. So here it is typically 300 MeV for this silver ion on gallium arsenide. Why silver? Silver has a lot of electrons to shed, so silver can be easily taken to 250, 300 MeV domain. So it was a particular experiment. It was calculated. It is shown. But if you change this this ion beam species, this peak will shift accordingly here and there. Height also and this thing. But if you take this energy per AMU here, then peak will be at such sign only as heavier ion goes, peak will go up. So that because actually velocity actually decides. That shows velocity decides. What happens when velocity is close to Bohr velocity for particular ion, then it actually maximum energy get transferred to the electronic system. So this is stopping power, electronic stopping power. It is called popularly. That is a SC, subscript E is given. So, but it is actually energy loss due to electron ionizing processes. And this is energy loss due to elastic collision with the atomic species. So these are the two important things. Why I am telling this will come again and again for different use, particularly biomedical and application. So that is a putting. This is a common one. Both this high density polyethylene actually this actually mimic our skin. So when we put human being, where ion is going, how it is treatment will go, then generally this calculation is done. Mostly these protons are used. So it is typical 205 MeV proton was used for some cancer therapy. Tumor was at the depth of around 27, 26 centimeter, 1 centimeter tumor was there. So for that it is a typical calculation. And Brookhaven National Lab, you can see the details. But this you can calculate sitting anywhere in your home or anywhere on a simple laptop. So nowadays, by using stream program and all those things. This is one thing where artificially these different types of gems are produced by doping different species on different hosts. Like if you put chromium in the Al2O3 as such as ceramic. So you put it chromium, you will see the beautiful this color comes. So then one can all kind of gemstones. And nowadays also a lot of people are using compact accelerators. Each accelerator for one type of gemstone. This gets fast filling. Actually, during formation of Earth, it happened naturally also. All kind of beams were there, all kind of temperature it went through. So it was a long process. But now quickly you like we make pearl artificially. Similarly, gemstones are made by this. That's why gemstones are now so cheap in Amazon site and other things. A lot of beautiful jewelry. Earlier it used to cost like anything. If you want to nature, it is rarely available here and there like diamond and all those things. So this, which I thought chromium, remember chromium in sapphire is ruby. Ruby is nothing, the earlier it used to cost like anything, nowadays it's cheaper. This is a nanocrystals of silicon. Silicon beam you embed in the sapphire matrix, you get nanocrystalline phase. You can see the facet, it is 2.6 nanometer. And then beauty is that one can make in chemically, but it is on the surface and you don't have control also. Here number of ions you can put, you can measure in the Faraday cup and you put the time. And at what depth you want, that is the energy you give. So that is the control. So how it works, this interaction process we see systematically time scale. I just told about length scale. This atom, when it moves to the nearly Bohr velocity, that electron orbit velocity of the external orbit will match with the ion velocity. It matches when 1/30 of a nanosecond. Means second means it will go 10 to a 9. Near light speed, 10% of the light speed, like that, to 15% domain. So it will match. It will start having maximum energy transfer and maximum energy loss. But what time scale it happens? It 10 to a minus 17 seconds. So because if you can see the dimension, and at this velocity, how much time it gets to cross this atom, one atom. Next atom comes, next atom comes, next atom, everywhere there and there. But the beam which is pulling the one atom closer to that, this atom I have taken for simplifying, other atom will come. But lattice, when you see vibration of lattice, you see in IR spectrum, FTIR, you know vibration. This takes place in the time scale 10 to the 12. So 10 to the minus 17 to minus 12 is a huge times lapse. So what happens to this? Actually, when this electron gets excited, it starts actually losing energy to the phononic, to the electron-phonon coupling, to the lattice side. And lattice side gets tremendously heated. And then this latent kind of activities happen. Initial days, the people used to give latent track. Name of the latent is inherent but not seen on a microscope. But later, when etching, there are many works from Kurukshetra also, Kurukshetra University, as well as NIT, from Punjab University, various groups all over the country, AMU, Delhi University, the latent track. And initially, we mapped the universe, this various trajectories around Earth, by putting this kind of polymer to study the latent track and see the kind of what kind of energy, because the latent track diameter depends on the energy of the beam also, how much energy is transformed, and what kinds of species are there around us, surrounding Earth. Luckily, most of them don't reach us, so due to this atmosphere saves us from them. But this is the process, fundamental process. And these time scales are taken care of that. Actually, finally, which we see in second scale. For us, these also very too fast. They are tremendous fast, like less than femtosecond also. So this scale also is IR scale. It goes to corresponding IR spectrum. From there, we study them generally. And what happens when this becomes too much heat is transferred? They start getting tremendous heated, and then form exotic phase, which when it is frozen, ion beam is from ion beam is there, it just gets highly charged. Electrons are taken away on the path. So it becomes highly charged as well as highly hot. Some of the heat transfer to the lattice side. So both Coulombic interactions and thermal spike, both are omnipresent. And depending on the conductivity of material, if heat transfers fast, then more Coulombic interaction takes place. If it is say insulator, then whatever heat cannot pass, it becomes superheated and it gets frozen to a state. It is due to mainly thermal spike. So there are major two processes in which this energy finally gets settled in the materials. And this can be calculated also. One electron system, one atomic system, if you solve these equations, you can calculate the spike and what kind of temperature it will give, depend on at what diameter also from the material and what time scale. Typically, lattice gets affected and the temperature gets established in a time scale of 10 to minus 13 to minus 12. As I told from qualitatively, quantitatively you calculate, you find that is correct. Because finally, quantitative thing gives actual value. And then depending on kind of whatever this diameter you are, as you increase in diameter, actually spike means temperature falls down there. So it is for 1 nanometer, 3 nanometer, like that in system. So this kind of latent track, how initially people used to do, they etch it, then it becomes much bigger than original size. Original, suppose it is fraction of a micrometer. After etching, it will be typically 100 nanometer, 50 nanometer, will become few micrometer. Then optical microscope, one could see them. And they say they are far away from each other by quite a few micrometers. It was easy to count them and see how many particles, and seeing the diameter, they could see what is a kind of species might have gone through that, what kind of ions are there in the this interterrestrial region, all those things. And nowadays, actually, TEM also gives quick and view, and AFM actually gives that this kind of structure which comes up. AFM gives in conducting mode, you can get a good feeling about it in direct space without etching. Because etching, one has to understand how much time actually one is etching. That has to be standardized also first with non-ion. But here you see directly in direct space, and without doing anything. So this is very important thing, is that now question was the accelerator ion goes everywhere, how to put it. GSI actually, they put huge amount of money. What they did, they put a ion beam on a small aperture, and by piezo they can see, change the sample. So they could see tracks, points are met, and within fraction of a micron to few micron distance each. The tracks can be controlled, and then if you etch them, you can fill it up with different kind of materials also, and one can have device. Actually, any device actually addressable. If you, until you make an array, it is not addressable. Until one can address the device, that PN junction or something doesn't have any meaning. So, quantum, when you do the calculation deeper level, at machine level, you actually play with the resistors, which are the locations where things are stored. Charges are stored, or magnetic field is stored. So this another big idea here, we contributed enormously in with even a lot of people from USA, Europe came to take our beam, is vortex spinning in high temperature superconducting materials. And in the 90s, I try to explain it to the particular new generation. It is so interesting. This actually cupid or the layer, and ion beam when passing through, actually it makes a series of defects. They are correlated. What is good about defect? In fact, sometimes people say defects are bad, but without defect, practically nothing could work. Like if you take a beautiful silicon perfect crystal and take around, nobody will use it because it has no use practically for device, for intelligent use. And otherwise, it can be used as a substrate maximum. But if you want, when you put a defect, means dope an atom to it, you make P or N type, then put close by, make a junction, then you put in series, you put a device. So all those things come when you put defect in the system. Okay. Any question? So this could be calculated also. We could see the silver beam which was available in our system. 200 MeV silver was making the vortex core, which is equivalent to the dimension of the coherence length in the visco. And for IPCO, it was 250 to 270 MeV. Both are available in our machine. So first we got a series of crystals from this Oxford lab, and there was some collaboration also, Clarendon lab particularly. And then we had collaboration with RRCAT for some measurements. So we showed that actually by pinning, you can make superconductivity effective, because ITC initially people are thinking it is of no use. Still today also people think, who are not knowledgeable about what is happening in the world. But if you see it is being used extensively, even from starting from transmission of electricity, intercity and all those things, plus particularly CERN accelerator probably could not come out without ITC, all this context. We also have a huge ECR and so ITC, space magnetics, all kind of space high TCs are being used. Initial high TCs were all perfect high TC. Film were made, and this used to HT curve. H, C, and J. Three axes are there within this. It is within that. If you take the phase diagram, within this curve, it is superconducting, it is non-superconducting. But if you put the beam of 10 to 11 particles, ions per centimeter, which take few seconds, immediately this moves to here. So what, for example, 25K, if I get around 1 Tesla field, I can make around typically more than 5 Tesla, typically around 7 Tesla field by same magnet. So like actually high magnet actually is to kill itself. So people, simple people got disinterested, but those who are sincere and knowledgeable, they kept working on that. What we did actually, we actually put the beam 200. This is 100 MeV, you can say. This 100, this is 200. So 200 is close to the peak. 270 is good for IPCO, we saw. Because here what happens if I put 270, the diameter of defect diameter is more than which is needed. The defect diameter makes that area non-superconducting. So the flux can move across. What happens, it is and all type 2 superconductors, those who have what's in MSc, this, they are actually, it is not perfect diamagnetic. It takes some field. So AC1, AC2 are there. After AC1, AC2, the domain is very not useful until fluxes are pinned. Other fluxons which are produced actually disturb the coherent motion. Superconducting current is a coherent motion. Cooper pair, they move together, mediated by phonon. So if this starts fluctuating, means non-superconducting zones start moving here and there, randomly produced, then they become a dissipative force. So if you can pin the flux, because some flux has to be accommodated in the system in type 2, they are pinned, they find some points which are, as I told you, this earlier also, oil is there formed. The beam actually pinning means oil is formed. The fluxon will stay here. Why do they spend more energy to go here? Actually, everybody wants to be a minimum potential, everything in the nature. So minimum potential positions are fixed in the system. Pinning is the fixing. Meaning. When we, as I told, ion beam wise the interaction I told, we can calculate and say 270 for IPCO. And actually IPCO is used for these cavities. All the microwave, all those communication, everything actually goes by cavities. The cavities are very important in science and applications. All communications everywhere, jamming, anywhere it needs cavities. So we could show 10 gigahertz cavity also, they are very useful. Initially there was a confusion, and with Maryland group also we could see there is a good pinning actually by this beam. We become quite famous. There are quite a few groups also working in various places, showed it. But we had a machine which can give silver beam easily, gold beam. Because most of the machines are designed, they can, a Calcutta machine, this cyclotron is not designed for silver or gold. And so they are mostly up to argon, typically they use. The design time you have to have all those processes. Another thing was shown in this came in Nature paper. This idea is how the electronic interaction actually making this process is done. They took a strontium titanate and different volumeter, different phase they could see. And when ion beam was put glancing it, this has produced maximum effect to that location where electron density is higher. It shows actually, which you told, electron interacts more strongly with the beam which moves at the swift avion, so-called. Swift avion means ions moving with velocity of Bohr velocity. That is how swift term came in it. Okay. So one could see the electron density, and those are the location. If I put glancing angle where it shows high density, the spots comes there. And this was shown. And highly charged ions, if you move lot of electrons out, when it comes near surface, these have nanostructure developed. These are being used for making detectors, also particle detectors, extensively by one company I know. And this process was physics-wise predicted, and now with high charged ion beam, this is put in this 97, around 1997, to theoretical studies. Actually, a lot of time theory predict fast, then we come experimentally. A lot of time experimental observation comes, then we explain by theory. It goes hands to hand. Both are important. But finally, anything we have to establish in science, it has to be theoretically, experimentally validated. And it is no question asked after that. So this kind of ion beam actually used for characterizing extensively Rutherford backscattering. This also elastic collision you have studied. So there is a kinematic factor. So one uses it. And nowadays what happens that actually you can produce helium or whatever ion you need with an accelerator. So one needs few MeV helium. One can put on the sample helium beam and a detector one can see backscattered. Example goes forward. The other backscattering, as I showed at the beginning, one can detect and see. I will show you later how it. Basic principle is that there are a few parameters. I will not go through details. You can see in the book. I will to shorten the time. So what is there? You can put the change in the energy of the beam to probe how much distance you want to probe, or what are the atoms available there. Scattering cross-section, different atoms will have. From there you can calculate the actual quantity of the material. The particular atoms are there. And mass determination comes from kinetic sector. What is the mass of the atom which actually causes the backscattering? Okay. So for example, one study is there. If you put gold on silicon and want to study its thickness, actually already put on. One thing is the cut it and put by this thing. Cutting is this precisely in sub-nanometer is difficult. So it is a rough estimate, but then you put a stylus, their accuracy is very low. And then this material is destroyed. But here you just put it in front of the accelerator to MeV helium, immediately you will see the gold peak and background. Actually, you are interested in this peak. From this width, you can immediately see it accurately what is the thickness of the gold. So these are non-destructive things. There are many things. I'll come a bit one by one, but quickly. Like platinum, cobalt, platinum, 3 layers on silicon, this multi-layer system. So one can see clearly the 3 peaks, how it comes. So you can see the this 2 platinum peak, because there Z is very high, and gold peak. And from gold, you can estimate the thickness of the gold. Platinum also separately you can estimate. Actually, depending on Z number, it will go higher. The Z number, it will go accordingly. And lighter background also, silicon background will be here. So, but silicon, one is not generally interested. But anyway, their peak is there. Silicon peak. And scattering of platinum is maximum, so that is the peak height is there. Gold accordingly. So if you have many layers, actually there is no other way practically. This is the only way to really study them. Here gold nickel, many layers put. And you see beautifully, you can see by Rutherford backscattering method, this thing. This is a great another process earlier people used to use. Now also it is much cheaper to use SIMS. But since you have to have a calibration, this is absolute calibrated, because these processes are physics process. Since you have to put particularly some standard, then take the scattering and then calibrate them. And when you do SIMS, actually sputters out, so it destroys. So after doing SIMS, your sample is gone. Okay, because one has to sputter and keep measuring them. So it will take long time, probably 10 hours or sometimes whole day to get it and then destroy the sample. Sometimes it can take a week also, depending on the case. And here within few minutes you get it, all the thing. Without disturbing, the sample remains as it is. So this is the message I want to see. This is a real one. In IUSC, there are quite a few in the country now, RBS system. Channeling also will come a bit quickly. So Rutherford backscattering, this is an accelerator, and then this is a chamber where it is measured. So this is the sample. A goniometer moves the sample, rotates accordingly, and detector actually this backscattered species goes, and you analyze it. And there are softwares also available, and all those things you can download and use it. This is actually how it looks inside the chamber, how the sample holder is there, how it is put, how detector is placed, where beam comes from. Here accelerator, a beam comes all the way. Okay. And there is a beautiful thing is called channeling. What happens, goniometer actually align the sample in different axes of the, crystals are having different axes, 100, 111, or like that. When you then when you exactly align perpendicular to beam, then instead of backscattering prominently, it goes inside because it gets an area open. Like if you really align the crystal in different area, you'll find all throughout open. So this is called channeling of the particle beam, high energy particles inside this process is called channeling. How it goes? It actually goes like that and get a different place. Through a potential, it gets through, channel through. And Reinhardt actually 1965 gave that idea. Now it is a standard process you can do in many places. Our center, IGCAR, Bhubaneswar also sometimes it works, and there are other centers. What are another prominent? IIT Kanpur also, they have machine for this. In fact, this Guru Ghasidas University, they are supposed to have this facility working. As soon as they are accelerated, they are working again on that. In between, it was off for some time. The backscattered particle actually, when you put randomly, backscatters. When you put in channel direction, these crystals are slowly rotated on a goniometer in such a way, these crystal axes are there going parallel to this. Beam penetrates deep inside, and few of them gets which are near surface area. There are some silicons, maybe silicon. There are some silicons, so the near surface area is not as perfect as inside crystal. So they have some randomness of scattering. So what happens? Scattering number decreases drastically. How it is shown? If it is random axis, same this gallium nitride. When you are not channeling it, just taking Rutherford scattering, it will be like that, which I showed in earliest picture many. And then as soon as you rotate and channel, it actually falls down like that. Then one knows this is a channel spectrum. Okay. And then on the surface, there will be some of them randomly placed. They will have very small scattering. But whole scattering actually falls down by a big amount. But what is the beauty? Why it is so? Channeling, it is fine, channeling happens. Beauty is that if you have any atoms inside the channel, there is an interstitial, you can immediately see. If there is a defect, one atom is moved, you can see channeling disturbed. And so you can go and define this channeling axis, and then finally found where the defect, this impurities at what level they are there. And there is no other, X-ray will never show you, because X-ray actually works by 2D sine theta n lambda. So X-ray doesn't see each and actually it is a K-space reformation of the spectrum. So if even you, for example, you remove from the top 10,000 atom, the X-ray spectrum will be same. Only intensity may slightly fall down depending on how many you are removing. And opposite to Rutherford backscattering is the elastic recoil detection analysis. Here projectiles come, you can see in the forward direction, slightly till the sample, and then this Rutherford backscattering heavy ion can be detected here, lighter ion can be detected easily with elastic recoil detection analysis. So these are the standard analysis process which are used for sample correction. So this is one very important application. In a developed country, there are companies who just give you all this data, do the experiment for you, and give the detailed specification. Like we test our water in India, they just give you all parameters of the sample and charge heavily, and they make use money. So, and then there is another method is PIXI, which is very important, biological all the samples. How many atoms are there? How many impurities? What are the things? Because PIXI, what happens when proton, typically it started with proton, but nowadays particles induce X-ray emission, they call. Earlier it used to proton induce X-ray emission. proton was earlier being used, but now a lot of species are available. More accelerator, versatile accelerators are available. When you bombard, actually different atom has different characteristics peaks. And then from intensity, you know how many impurities are there, how much impurities, what are the impurities. Rocks, metals, water, anything you take and bombard the beam, you get X-ray. This is typically example of X-ray, typical X-ray spectrum. So you can have a standard spectrum control and see and you can calculate the cross section, scattering cross section, and exactly give the density as well as species of the materials. But channeling actually works differently. At what length, this is actually gives us presence of the materials near the surface. Okay. From deeper shell it comes, but each material's K, L shells are different to each atom. So that signifies the atom from characteristics X-ray. You can see what atoms are there. And then this elemental, standard elemental analysis are done by companies also. There are. Actually, this Pixie is now a very favorite standard for people working in the environmental science and biological science, and getting the number impurity atoms, number and impurity atoms, and what are the atoms to understand that. But in a crystal silicon, you know already what atoms are there. You will not go for Pixie. You will go for other things when you are doping. And there is another field which is extensively used all over the country is mass spectrometry to go get history. So carbon is typically done to carbon lifetime is carbon 14 is typically 5,700 years. Typically 10 times you need 57,000 years typically back. You can do 10 to 12 half-life actually one can measure. If you want to measure to millions of years, the glaciology and all those things, people can use beryllium. This is used for archaeology, anthropology, all those things, or botanists, all those people they use. And this is used actually for this thing, and multiple billion years also sometimes one does, depends on what kind of materials, aluminium. These are actually radioactive isotopes. To stable isotope ratio gives the years. So iodine actually gives even tens of billions years accurate data. So all these facilities also now we have in India. Earlier we didn't have it 10 years back. Okay. So now it can be done in our site also. IUSC, this one tandem is completely dedicated for this. There is one in Bombay, one is PRL, Ahmedabad. There are a few, and others are coming. So you can have the ion beam and go to the accelerator. Accelerator beauty is there. Earlier, Aston mass spectrometer was being used. Aston mass spectrometer typically used to give the accuracy 1 in 10 to 8, and this accelerator gives 1 in 10 to 16. So very accurately, that actually gives the date. When you give a date and how accurate it is. You give, suppose 50,000 years back date, you can give within few hundred years, this side, that side. And that is very important. This is physically how it looks like. This accelerator, the analyzer, and this is the answer side. This accelerator mass spectrometry. It actually can carbon 13 to 14 ratio also comes. Typically carbon 14 and carbon 12 ratio gives the lifetime. If you see the ratio, you know when the system was dead. Because a live sample will not have, which are modern samples, today something is made of carbon, they will have this differently. Then after 1,000 years or 10,000 years, this will start, physics is that this will keep decaying, going down in concentration, this will remain same. So ratio will fall down. From there actually we get the date. I will not go much into it other than that. This is a kauri wood which we have done, and we gave the date depending on different, this is from New Zealand, we could give the date line about 45,000 to 50,000 years back, 3 samples. And this actually, the company also tries to, this is from Titan, and they also try to get from 2-3 sources. Because these are always, we also tested our machine with standard samples with other top AMS centers in the world. And we actually, IUSC is stamped, IUSC accelerator only stamped. with this perfect data within the error band. So IUAC-D it is called. So these coriodes are used for all kind of beautiful product, costly system. And if there is a Rakhi Gari, in this Haryana, there we did the AMS studies and so that there are different dates. What are the dates we have given? That also they are matching with other historical evidences. This is one beautiful thing which gives a lot of publicity to AMS for common man. There was a shout. It was claimed to be of Jesus Christ. So this AMS and various labs came found actually science gives the same result. Like PN junction will work same as in Russia or USA or India or Bangladesh. Similarly, this dates found when we do it correctly, it is within 0.5, 0.2% accuracy, similar date. It was found 1300 years back. So it cannot be Jesus shout, which was claimed that Jesus is coming, all kind of things are claimed. And this details came in Nature also. So, this somebody is the application of biology, big application today is coming where tens of thousands of persons are getting fully cured. This is called head-on therapy. What is that? As I showed you a picture, ion beam actually typically have this curve. But this state of the curve actually depends on one beam. The proton, it is slightly spreaded. If you have carbon is about 5 times costlier, is having much sharper. Where you have somebody has a problem, this is a typical case of brain tumor surgery is shown. There's about 15 centimeter inside the tumor is there. Well, if one goes the X-ray, this maximum hospital gives X-ray, this thing. X-ray problem is that it actually spoils the skin as well as spoil. This much energy is given to the tumor, but on the way, this much energy is spent on the skins, on the path. So actually, person gets severely affected. It is well above threshold. Threshold is typically around this energy. It can take absorbance of around 40% it can repair. But after that, it actually, gamma also peak is slightly shifted, but gamma also actually spoils the path. But this black peak, as I told, it is called actually, in nuclear physicists mostly use the term bragg. The bragg peak actually for this thing is there, we can increase the energy and the peak can be anywhere, here to here. Wherever there is a problem, peak is put there. And beyond peak, it is lower than that. As I showed at the beginning card, it goes slowly and peaks at the particular, depending on the energy inside. So this is if you put it there and then rotate this person on this rotating system, actually tumor is bombarded from all angle. Tumor is totally cured, and no chemical, no drug, nothing, and no chemotherapy is needed. So physically, actually, it shows like this. So this first tumor has to be MRI scan. It is not spherical ever. So one has to take a phantom and do the calculation for simulate on the phantom, and then phantom is checked, everything is fine. Then human being is put. Actually, a lot of protocols are there, but typically 1 hour, 1.5 hour, one human being takes. And after this, actually, people have found that this actually it is 100% success. If the person doesn't mess up, because if it doesn't go in time, it's spread everywhere, then you cannot keep on bombarding everywhere. It is like if cancer spread everywhere, then it becomes difficult. If it is localized, then that locality, it can be killed at that location without any effect on the skin surrounding. A switched up, actually here it is below threshold, here actually threshold. It goes above threshold. Those cells are destroyed. And example is given within 6 hours, person could die or go around fully cured. There is no, after chemo actually is different. It goes everywhere and affects everything, even hair and all kind of thing. But it is much cheaper and available easily. Here, actually, these facilities we are working for quite some time. It is slowly coming up in the country. We can also build it, and I think in Jajjar also it will be another 5 to 7 years it will be there. But already it is there in Chennai. Another is coming in Tata Memorial in Mumbai. Order is placed. This is a new kind of materials which we did with the Singapore University Group. This is our work where we showed actually by RBS we could see the oxygen layer, actually how corrected it. And then one could see varying the hydrogen we could control, reversible control, and any antiferromagnetism actually follows their theoretical prediction that could be achieved by experimentally. And so there is a big site you can go and see in the International Atomic Energy Agency site. They are actually future technology bringing quantum technology with ion beam. They are predicted big way. A lot of works are going on. You can see I cannot cover all of them. I can show one of our work where we have shown large area we can have this nitrogen vacancy related issue in silicon carbide. Silicon carbide is hot today, like zinc oxide was 20 years back. So nowadays it is day by day hotter because due to quantum materials related issue. So 100 MeV silver, with that we could show this. But recently, last year, very important this data has come from this Lawrence Berkeley laboratory, is that they could make 10,000 coupled qubits over a distance of human hair by putting ion beam. And our beauty is that, as I showed you, ion beam actually, that is why I showed that Nature paper. Ion beam actually affects when density, electron density fluctuation. If you see in sub-atomic scale, Fermi, that scale you take, then you see inside the solid, the electron distribution is big changes are there, and depends on correlation and the structure and the effect. If structure is distorted also, or some atoms are put inside DOP. So that kind of scenario in diamond, we could put these color centers could be produced also in ion beam systematically. Actually, correlation is important. The correlated defects are coupled, they can couple together within distance required. So this is going to emerge in a big way in the next few years. You will see, and the quantum computing will revolutionize everything in the world in crypto and all directions. It will be revolutionized. And already there are some quantum computers working. Google started the game, and then in a big way. So the combination of wide varieties of ion beams at various energies and charge states actually gives us a lot of flexibility of thinking, working in the direction for future research, and establishing, understanding the process. By the way, we have to keep publishing also to survive and produce new manpower. They will also add to the value, add to the new thinking. This understanding and control, actually reproducibility is very important. As we go in lower and lower dimension, actually we have to reproduce also that level. Suppose I am making a building, we are having meter as the dimension. So small variation here and there in the wall, few micron or few hundreds of micron also will not be seen. But in that in atomic scale, even a few nanometers is a big thing. One has to, accuracy level has to go, reproducible to go to that level. So I would like to thank a lot of all my students, scholars, and collaborators, colleagues. We on this path we worked with many people at many levels, learned from them, discussed with them. We talked, shared our ideas, and that is how we develop with time. We enjoy doing science and enjoy reading others' contributions also, and I can appreciate that. Thank you.
Thank you, sir, for a wonderful presentation. But I think that it's so. I request all the students who are interested, who have questions in the chat box, they may write an email to you directly for with their queries,
Yeah.
because due to time constraint, because students have their lunch hours in their mess. Sir, so I would request the students to write to you via email. Okay, sir?
Feel free to write, and I hope you will be after that continuing in your career in science and go further. And we will also learn in future many things from you, from your work. This is a real building up process, and always we enjoy
Yes, sir.
seeing students doing more than us. Okay, so thank you. And
So now, a vote of thanks. So now I found but delegate duty to propose a vote of thanks on behalf of the Department of Physics and on my own behalf. So at the outset, we express our sincere gratitude to Dr. Kanjilal for accepting our invitation to grace the occasion in spite of his very busy academic and administrative schedule. We are indebted to you, sir, the university in general, and we, the investigators of this project, namely Professor Sanjeev Agarwal, Professor Shyam Kumar, and myself, in particular, appreciate from the core of our heart the commitment and devotion of the IUC team, including yourself and Dr. Sandeep Chopra, to the task of strengthening the ion beam-based research activities in the country. We are also thankful to Department of Science and Technology for funding a project to establish this ion beam center at Department of Physics and University. The organization of this function could not have been simply possible without the able and invaluable guidance and wholehearted support from our worthy Vice Chancellor, sir. So we are extremely grateful to him for being an inspiration for us at each and every stage. Thanks are also due to Registrar Kurukshetra University for extending all the administrative support. I'm thankful to Professor Fakir Chand, Chairman Department of Physics, for his constant encouragement and moral support. I'm also thankful to the faculty members of Department of Physics for their wholehearted involvement in organization and management of this program. Research scholars, non-teaching staff, and students of our department also deserve a special mention for their efforts for making this program a big success. So thanks a lot and have a nice day. And I would ask or request all the students to come for their regular classes at 2 o'clock. All the students of MSc classes, they come for their regular classes at 2 o'clock in their labs as well as in the classroom. Because I'm getting message from a lot of students that what is the next schedule, so your regular classes will be held from 2 o'clock.
Thank you, sir.